Hello friends, today we will be discussing the basic principles of resonance theory. The resonance I will explain with an example. Say in the case of an anion of this nature, HCONH minus, this anion, we can represent this anion. The structure can be drawn in two different ways. Two valid Lewis structures can be drawn. Okay, Lewis structure. You know what is Lewis structure? Lewis structures are electron dot representations of molecules. Okay, so two valid Lewis structures can be drawn for this anion. So one will be like this, HC double bond O Okay, this is one structure. That is, there is a carbon-oxygen double bond. Then there is a negative charge over the nitrogen atom. Correct. There is another structure which we can draw. Okay, these are the two structures, valid Lewis structures we can draw for this anion HCONH minus here. In the first structure, that is structure A, we can call it structure A, and this is structure B here. Okay, first structure, there is a carbon-oxygen double bond, and there is a negative charge over the nitrogen atom. So in the second structure B, there is a negative charge over the oxygen atom and a carbon-nitrogen double bond here. Okay, these are the two structures. That means some molecules or some ions, we cannot adequately represent it by using a single Lewis structure here. Okay, structures of some molecules that can be represented by more than one valid Lewis structure here. So the actual molecule here, it is neither A nor B. Okay, it is a composite of A and B here. Actual molecule, it is not accurately represented by any one of these Lewis structures here, either A or B here. Okay, but it will be more accurately represented by a combination of two or more Lewis structures here. That is, the actual structure of this anion, it is neither A nor B, but it is a combination, some kind of a combination of A and B here. Okay, that is, some molecules we cannot adequately represent by a single Lewis structure here. That is, here, in this case, for this anion, we can draw two valid Lewis structures here. It can be drawn for this anion here. The structure A, it has got, it has a negatively charged nitrogen atom and a carbon-oxygen double bond. And in the second structure B, there is a negatively charged oxygen atom and a carbon-nitrogen double bond. These structures are known as resonance structures here. Okay, now these structures are called resonance structures here. That is the difference here in this structure. Now these structures, resonance structures, to represent these resonance structures, separate these two structures, we are using a double-headed arrow. Okay, there are different kinds of arrows being used in organic chemistry here. Here, to separate two resonance structures, we are using a double-headed arrow. This is the double-headed arrow. Two heads are here for this. This is the way we are representing the resonance structures here. Now, here the difference here, it is actually, what are these resonance structures here? That means Lewis structures that differ only in the location of the electrons here. Non-bonding electron pairs as well as the pi bond electron pairs. There is a difference in the position of the electron pairs here. That is non-bonding electron pairs here as well as the double bond, that is a pi bond electron pairs. Okay, these structures are the resonance structures here. That is structures which differ. Here the position of the atoms are the same thing. There is no change in the position of the atoms, but the position of the electrons are different here. Okay, that which kind of electrons? Non-bonding pair electrons as well as the pi electrons. That is a multiple bond electrons here. Okay, that is why these structures, one the carbon-oxygen double bond, carbon-nitrogen double bond, and negatively charged nitrogen, negatively charged oxygen here. Therefore, these two Lewis structures that differ only in their position, location of non-bonding electron pairs and or pi electron bond, pi bond electron pairs. Okay, they are resonance structures here. Now a combination, that is some kind of a combination of these two structures, we can say that is called a resonance hybrid here. Okay, now the basic theory, basic principles of resonance theory. Okay, it is actually these structures. Now here we have drawn A and B here. These are not real structures here. Okay, real structure is a combination. That is what we want to say. These are all imaginary structures. Okay, these resonance structures they are not real structures. They are fictitious structures. Okay, they are imaginary structures, we can say. So an individual structure, resonance structure, it does not accurately represent the structure of a molecule or a structure of a ion. Correct? Only the hybrid. The hybrid means resonance hybrid. So, okay, the resonance hybrid, individual resonance structure does not accurately represent the structure of a molecule here. So, the hybrid means it is some combination of the individual resonance structures here. Okay, now we are using a double-headed arrow here. It doesn't mean they are in equilibrium. People may mistake that these two structures A and B, they are in equilibrium. No. The double-headed arrow doesn't mean it is in equilibrium. Resonance structures are not in equilibrium. That is, these structures do not move backward and forward in the case of an equilibrium reaction here. Okay, so the resonance structure, it do not shift back or do not shift in the front. Okay, as in an equilibrium reaction. Therefore, there is no equilibrium. They are not in equilibrium with each other. There is no movement of electrons. Okay, there is no movement of electrons rather from one form to another form here. Okay, that is another point. Now, the next one is that the resonance structures, they are not isomers. Okay, what are isomers? They are not isomers. Resonance structure, isomers are compounds with the same molecular formula, molecular weight, but different structures. Okay, that means the connectivity of atoms will be different. The position of atoms are different. The position of electrons are different here. In the case of isomers, the different arrangement of atoms, different arrangement of electrons. Whereas in the case of resonance structures, you should know that the position only in the arrangement of electrons. That is the position of the electrons is different. Okay, therefore, resonance structures are not isomers. Okay, that is, isomers differ in the arrangement or other position of atoms and electrons, whereas in the case of resonance structures, the difference is only in the arrangement of electrons. Okay, now resonance structures mean the compound is same. There is, just like isomers. Isomers are different compounds having different physical and chemical properties and all, that. But in the case of resonance structures, this compound is the same thing. There is no difference in the compound. Actually, these are the different ways of drawing the same compound. Different ways of drawing the same compound. They are not different compounds here. Say, if you take these two things, these are one structure of this kind and another structure of this kind. Okay, there is a positive charge here. Then, okay, here, these two structures, they are resonance structures here. Okay, because one electron pair, it is in a different location. In both these structures here, Ca3CO triple bond and Ca3C double bond, the position of the electron pair is different here. Therefore, these are resonance structures. These are resonance structures here. Now, that is structure of the same compound. Okay, now if you take a compound of this nature, CH2 double bond, then C OH, there is an OH group here. Okay, then CH3, this compound and this compound. Okay, these compounds are different compounds actually. You see, one is having a hydroxyl group here and the other one is having a carbonyl group here. Okay, keto group. Therefore, and the structure number 2, this is structure number 1, this is now structure number 2. Structure 1 is having an OH group. Here there is a carbonyl group. That is, the functional groups are different here. And here it is CH2 double bond COH. Here in this case there is an extra CH bond is here. Okay, one extra CH bond and one OH bond the other one. Therefore, these are isomers. They are different compounds here. So this is the difference between a resonance structure and an isomer here. Okay, now another example. If you see, there are two compounds with the same structure. If you take this compound here, CH3, oxygen, CO, then this compound here. Okay, so this is this one structure, and another structure I am drawing here, CH3, CH2, then C double bond O. Okay, OH, correct? So this compound here, these are isomers here. That is, you can see the molecular formula. This is a C2, C3, C3, H6, C3, H6, O2, correct? So this is also C3, H6, O2. Therefore, these are isomers here, having the same molecular formula, correct? So these are isomers here, correct? Now, if you say, now this compound, that is, we are using a double-headed arrow to draw the isomer here, CH3, CH2, C, then here it can be minus. Okay, then okay, these are resonance structures here. The position of the double bond is different, and the position of the non-bonding electron pairs are different here. These are resonance structures. So in the case of isomers, the difference is in the position of atoms, position of electrons here. Whereas in the case of resonance structures, the difference is only in the position of electrons. Okay. Therefore, now we have seen structure A and structure B. In the beginning, we have seen that anion. So that neither that structure, it is a true representation of the anion. Okay, these two anions we have drawn here in the beginning, that is HCO, this is the anion we have started with. Correct. So this is the one structure, that is resonance structure. The placement of atoms, it will be same, but different arrangement of electrons here. Okay. Now, a double-headed arrow we have put. The other resonance structure will be C double bond N, correct? So these are the two resonance structures we have drawn here. Now we have seen that neither of the structure, it represents a true, it is a true representation of the anion here. Okay, the true structure, it will be a composite. That is a composite of both the forms. A combination, some kind of a combination of both the forms of these structures, that is called a resonance hybrid here. Okay, now the resonance hybrid, it shows the characteristic of both resonance structures here. Okay, now in resonance, what is actually happening? it is the certain electron pairs, they are getting delocalized. Okay, delocalization of electron pairs. Is a very important point. So this will add stability. You see, when the electron pairs, they are not stationary on a particular one atom, but it keeps on moving. Okay, that is getting spread. Electron density is getting spread over 2 or more atoms. Okay, this delocalization, it is known as a delocalization of electron density, delocalization of electron pair. It will add stability to the molecule or stability to the structure. Okay, as a molecule with 2 or more resonance structures, it is said to be resonance stabilized. Correct. Now, a resonance hybrid, we will discuss resonance hybrid subsequently. So here the delocalization, that is the electron pairs or electron density is getting delocalized over 2 or more atoms here. And this delocalization, it is adding stability. That is, this is called a resonance stabilized. So we will say the structure is resonance stabilized when the electron density is delocalized over 2 or more atoms here. Okay, now we can see the rules for drawing resonance structures. Now, how will you draw the resonance structure? So, the two resonance structure, the important point we'll have to see is when you are drawing the resonance structures, the first thing you should remember, there is no change in the position of the atoms here. Atomic position remains the same thing, correct? But only the electron, the position of the electrons, it will be different. No change in the position of the atoms in the Lewis structure, correct? That is how we will have to draw. When you are drawing, that is a fundamental principle. That is, two resonance structures differ only in the position of either in the multiple bond. That is the pi electrons here or a non-bonding pair of electrons. Correct? That is the difference in the position of the multiple bond and non-bonded electrons. Non-bonding pair of electrons here. Now, the placement of atoms and the placement of the single bonds always remains the same thing. Okay. Now here in these two structures we can see the position of the double bond is different here. Now, position of the double bond is different and the position of the lone pair of electron, non-bonding pair of electron, it is different here. Okay, these structures A and B, it is the thing. This is structure A. We can just mark it here. This is structure A and this is structure B. We can say the position of the atoms, it is the same thing. There is no change here. The position of the double bond is different. Okay. That is a multiple bond, the position, it is different. The position of the lone pair, that is a non-bonding pair of electron, it is different here. Okay, now another rule here is, you see the resonance structure must have the same number of unpaired electrons here. Unpaired electrons, okay, number of electron pairs, it will remain the same thing in each structure here. Okay, then the resonance structure must have also the same number of unpaired electrons. Now, if you draw a structure like this, it is not a resonance structure. HC. Now, one single electron here. This is an unpaired electron here. And here, in this oxygen atom, we are writing one unpaired electron here. Okay. Now, if you draw a structure of this nature, it is not. That is, this is C. This C is not a resonance structure of A and B here. A and B are no unpaired electrons are there. Whereas in the case of C, there is an unpaired electron on the carbon atom. Correct? That is, this is not a resonance structure of A and B here. Okay. Now, rule 3. Rule 3 means it should be a valid Lewis structure. What is valid Lewis structure? You have seen Lewis structure. They are the electron dot representation of molecules or ions. Okay, that is the valence electrons are displayed there. And another point is hydrogen atom. Hydrogen must have 2 electrons only. And an element in the second row of the periodic table cannot have more than 8 electrons. That is a fundamental thing. That is rule 3. When you are drawing resonance structures, you have to see this should be a valid Lewis structure. Now, suppose we draw a structure of this nature here. See, if you are drawing a structure like this here, HC double bond O. double bond NH here. You see, it is not a valid Lewis structure here. Okay, that is, there are 10 electrons around the carbon atom. There are 10 electrons. Therefore, it is not a valid Lewis structure. Therefore, you cannot draw any resonance structure for this kind of a thing. Okay, so these are the fundamental things, fundamental principles of resonance theory now. Now, we are using another notation here. You see, you keep adding so many arrows. This is curved arrow notation. What is curved arrow? Now, we have seen a double-headed arrow. Now, this another arrow I am going to introduce. It is a curved arrow notation. That is, the arrow like this is a curved arrow, or this like, if you write it is a curved arrow, that is, there is a head here. This is the head of the arrow, and this is the tail of the arrow. Okay, so these kind of arrows, what for we are using? Curved arrows, they are used, it is a convention that will show the electronic movement here. How electron, you see, show the electron movement here. It indicates the direction in which the electron is moving. Electrons on the base of the arrow, that is a tail. It is moving towards the head, That is, it shows the electron moving, the tail, from the tail to the head, actually. Curved arrow notation shows the movement of an electron pair. The tail of the arrow, it always begins at an electron pair. Okay, this electron pair, it can be either in a multiple bond, pi bond, or it can be a lone pair of electrons here. Okay, it is a convention. It is used for showing how electron positions they differ between two resonance structures here. Okay, it shows the movement of an electron pair here. It shows the movement of electron pair. Okay, it indicates the direction of movement of electron pairs from the base of the arrow, okay, to the head of the arrow. Okay, now we can say actually the electrons are not moving. In most cases, they are shared in covalent bonds here. This is simply a convention. Okay, now the electrons movement, it does not necessarily mean that electrons are actually physically they are moving from here. Okay, we are just indicating the movement of the electron, how the bonds are formed or changing, that is all. Okay, therefore, and normally the electrons, they move from from an electron deficient site. We have an electron deficient site and an electron rich site here. Okay, from the electron rich site, the electron moves towards the electron deficient site here. Okay, the electron deficient site never moves towards the electron pair. The electron pair moves in the other direction only. Okay, therefore, that is one way of drawing this structure now. Now, the head points to where the electron pair moves. Okay, now, resonance structure here we have drawn resonance structure A and B here. First, now we can draw the difference only in the location of the two electron pairs here. Now we can show the movement of the electrons here. How we will show the movement of the electron here? You see, this electron pair in the pi bond, it moves like this. Okay, then this lone pair, it will move like this. That is why we are getting a double bond here. Resonance structure A and B, the difference is only in the position of the two electron pairs here. Now, two curved arrows are needed because, the electrons in the pi double bond and electron lone pair on the nitrogen, they are both are moving. So, we are using two curved arrows here. Okay, so lone pair of nitrogen atom and a double bond character. It forms a double bond between nitrogen and carbon, or carbon and nitrogen, whatever it is. Then an electron pair in the CO double bond, it is moving. Actually, okay, curved arrows are used for this purpose. So to the repositioning, okay, curved arrows are used for representing the repositioning of electrons, okay, in converting one resonance form to the another form. Electrons themselves do not move actually. Okay, now use this electron pair. This electron pair, it is used to form the double bond here. That is the electron pair on the nitrogen. It is forming a double bond here, and here there is a minus charge. Okay, so individual atoms keep exactly the same positions here. That you should see. Now all resonance structures, only the electron pairs move here. Okay, two different resonance structures can be drawn. We can draw in this fashion. That is the movement of the electron pair, we can say. That is, individual atoms, they keep exactly the same positions here. There is no change in the position of the individual atom. In all resonance structures, only the electron pairs are moving. Okay, now two different resonance structures. Now we can draw. I will just show you two different situations. Rather, one situation will be a lone pair. It is located on an atom directly bonded to a multiple bond. Now suppose we are having a structure like this here, CH2 double bond CH. Okay, now CH2 minus. Okay, a structure of this nature, that is a lone pair here. This lone pair, it is adjacent to a carbon-carbon double bond here. This is a minus charge here. Okay, so now here the electron movement will be like this. That is from the pi bond, double bond, it will move like this, and this lone pair, it will move like this. Okay, so what will be the nature of the structure? The other structure will be double-headed arrow here, curved arrow, double-headed arrow. Okay, so CH2, so there will be a minus charge because the electron pair is migrated. Okay, CH, then a double bond over here. Correct. This is one way of showing these electron pair migrations here. Correct. Electron movements. Now another structure, if you see, that is a lone pair adjacent to a double bond here, carbon-carbon double bond. Now if you take another compound here, CH2, then this is a minus charge, correct? Then an oxygen. I know this is C double bond O, CO. Okay. CH3, correct? Now the lone pair, it is adjacent to the carbon oxygen double bond here. Therefore, how this electron migration will take place? This lone pair, it will go like this. Then here in the double bond, it will go like this. Now the new structure will be CH2 double bond C O minus. Okay, CH2 double bond CO minus, then CH3. This will be the new structure here. Correct? That is lone pair adjacent to the carbon oxygen bond here, CO bond. So the electron migration, we can show it in this fashion with the curved arrow notations here. Okay, now some other more examples I can give you so that you will be thorough in this subject. So an atom bearing a positive charge, it is bonded either to a multiple bond or an atom with a lone pair of electrons here. See, one simple example I can show, CH2 double bond CH. Okay, then CH2 plus. This is a carbocation. Okay, carbocation are unstable species, which is a positively charged carbon atom here. It doesn't have an octet. Therefore, it is highly unstable. So it is a species carbocation here. Here there is a positive charge. This positive charge is adjacent to this double bond. Therefore, the possibility is here. From this pi electron, it can go like this to this side. That is the positive site. Okay, so we will be getting another structure here, that is CH2 plus. We have to assign a formal charge here, assign formal charge of +1 for this carbon atom here. Then we have CH double bond CH2 here. Okay, this is one way, this thing, that is a positive charge. It is adjacent to a double bond here. Okay, atom bearing a positive charge is bonded either to a double bond or multiple bond or atom with a lone pair. This is the situation here. Okay, CH2 double bond CH2 plus carbocation. So it is becoming CH2 plus this side here. Okay, so long as the Lewis structure is the correct thing, there is no problem. Okay, now another thing, another example is CH3. We can say a lone pair on the oxygen. We can have like this. Then CH2 plus. If you have a structure of this nature, what will happen? This lone pair, it will go like this. This lone pair will go. Then the resonance structure will be, how it will look like? CH3 O will become plus here. Okay. Then there will be a double bond here. Okay. CH2 here. Correct. That is positively charged. It is adjacent to a atom with a lone pair of electrons here. That is, oxygen is having a lone pair of electrons here. Atom bearing a positive charge. It is bonded either to a multiple bond or an atom with a lone pair here. Okay. Now this is the way the curved arrow notations are being used here. Now if you want more examples, I can give this, explain it with the help of some more examples here. Say H, C, that is CH2, correct? CO double bond CH3. Okay, the structure of this nature, that is CH2, that is minus, then CO CH3. Now the resonance structure, it will be how the electron migration will be there. This lone pair, it will migrate here, correct? And then this will go like this. Okay, so the structure, the resultant structure will be H, C, H, double bond, okay, C, O, minus CH3. What is this? It's a very important anion here. Enolate anion. It is known as enolate anion. It's a very important in the organic synthesis. We will be discussing this thing all in detail later in our other classes. CH2, CO minus CH3, enolate anion. You see, there is a formal charge, oxygen, formal charge is -1. Oxygen, -1. Okay, this is the thing. So, and another example, if you take a carbonate anion, again, you can keep practicing, by drawing so many anions and cations and all these kind of things, so that you will be thorough. Say, if you take an anion of this nature, this is what is this? This is carbonate anion, correct? That is CO3 minus. Oxygen has a formal charge of -1 here, -2 here. Okay, carbonate and calcium carbonate and all we have seen now. So here it will be 6 electrons, 3 pairs. Okay, so minus charge, and here also same way. There is a minus charge here. Okay, now the structure will be, we can draw 3 structures in this fashion. Now this thing, it will be migrating like this. Electron we can show like this. Then this lone pair, it will go like this. Correct? So we can draw another structure, that is this carbon, this becomes minus. Okay, then here there will be a double bond. Oxygen double bond. Then this will remain the same thing. Minus here. So the next movement of electron will be So this can go like this, and this will go like this. Okay. Therefore, what will be the nature of the structure? The third structure will be carbon double bond will come here. Then this remains same. Minus. Here also same thing. Okay. This is the carbonate anion here. Now here, what is important here, what you have to note here is the delocalization of electron pairs here. Okay. So delocalization of electron pairs, just like delocalization of a positive charge or a delocalization of a negative charge. Okay, it increases the stability here of that particular species here. Okay. Now, electron pairs, they are not localized. You see, localization and delocalization. Localized means it will be sitting on a particular atom all the time. It's not doing like that. It is delocalized. That is, it is getting spread over 2 or more atoms here. Okay. Therefore, the stability of this particular anion or particular molecule, it increases. Okay. So, now we will be discussing a resonance hybrid. What is meant by a resonance hybrid? So resonance hybrid we have seen, that is resonance hybrid, it is a combination of all the possible resonance structures. Okay, now the hybrid is, it will more closely resemble the most stable resonance structure. Okay, there is a concept called most stable resonance structure. Resonance structures means which is more stable, which is less stable, which is equally stable. There are 3 different situations here. So the resonance hybrid means it closely resembles the most stable resonance structure. The first thing. So the most stable resonance structure, that will be the major contributor to the resonance hybrid. Okay, it's a major contributor to the resonance hybrid. Okay, that will be the most stable resonance structure. That is the resonance structure. It will resemble mostly to the major contributor of the resonance structure. That will be the most stable one. The other one is the major contributor. Then it will be a minor contributor. That is the less stable one. Okay. Now, if 2 structures are identical, equally stable, then they are equal contributors. Okay, there are 3 concepts like this in the case of resonance hybrid here. Okay, that is resonance hybrid means it is some kind of a combination of all of the resonance structures. Okay, the hybrid, it will be more closely resembling the most stable resonance structure. Now, the most stable resonance structure, it is called the major contributor to the resonance hybrid. Okay, now the less stable resonance structure, it is the minor contributor to the resonance hybrid here. Now, identical resonance structures are equal contributors. Okay, now resonance hybrid, it is more stable than any resonance structure because there is delocalization. We have seen, in the case of a resonance hybrid, there is delocalization of electron density. Okay, therefore, a resonance hybrid, that is the more stable one. Because why? Because of delocalization of electron density. Okay, over a large volume. Correct? So in the case of this carbonate anion, we have seen that electron density is getting delocalized over a large volume. Therefore, the resonance hybrid, that hybrid will be more stable. And there are 3 things: major contributor, minor contributor, equal contributor. Okay, now in the case of, we will come back to our anion, how we will draw a resonance hybrid here. Roughly, I can just show you that is HCO. There are rules actually for resonance hybrid also. Before that, I will just show you. This is how the resonance hybrid is being represented. See, HC, we have seen HCO and H, I think. Yeah. This is the anion we have been discussing in the beginning. Okay, this anion. Now we have seen the resonance structure of this anion. Double-headed arrow here. O minus. Then a double bond here. H. So these are the two individual resonance structures. Individual resonance structures are also described as a canonical structures here. Canonical structure. Okay, it's so this is the individual resonance structures here. Okay, now the hybrid will be, what will be the nature of the hybrid here? Hybrid is the most stable one because of the electron delocalization. Okay, now we can show this hybrid. Hybrid, there will not be any double bond, there will not be any negative charge. Then what? The oxygen position of the atoms remain same. Okay, now we will be putting in the, there will be a partial negative charge here. It is represented by delta minus, and here on the nitrogen also there will be a partial negative charge here, and we will be putting this double, instead of double bond we will be putting some dashed lines here. Okay, like this. So this is the resonance hybrid of this anion. Okay, the dashed line, it indicates the partial double bond character because the double bond was initially carbon-oxygen double bond, and in the other structure it is carbon-nitrogen double bond. Therefore, the double bond character is carbon-oxygen, carbon-nitrogen. We are just showing it here, use the dashed line here. That is partial double bond character. And the negative charge, in the first structure, negative charge was on a nitrogen, and the second structure, the negative charge is on oxygen. Therefore, we are showing a partial negative charge, delta minus. Delta minus for partial negative charge, it indicates the charge, it is delocalized on the nitrogen atom and oxygen atoms in the hybridized form here. That is delocalization of the charge. Okay, that is the negative charge, it is getting delocalized on the nitrogen and oxygen. That is the lone pair of electrons. Here the electrons in the pi bond, that is a double bond, and electrons on the non-bonded electrons, non-bonding pair of electrons on the nitrogen atom, they are getting delocalized here. Okay, so this is how we are drawing a resonance hybrid. Okay, now simple rules are here for even for drawing a resonance hybrid. That is, the hybrid, it will look the more stable hybrid, the more stable structure it will look like, and the hybrid, it will look like similar. Okay, that is, the hybrid looks more like the more stable structure. Okay, now if you have a structure of this nature, CH3, C, then we can put a double bond, CO. Okay, a compound of this nature here. Okay, if you are having a compound of this nature, so the electron, it will get shifted here. That will be the resonance structure for you. The structure will be okay, this is the thing. There is a charge separation here. Okay, now as per the rule 1 of the resonance hybrid rules, there is nothing called a resonance hybrid rules as such, because for drawing this resonance hybrid there are certain set of norms here. Okay, now the structure with a more bonds and fewer charges, it will be a more stable structure here. Correct? Now here in the first one A and second one B. Now second B, if you see it, the first one A, only bonds are there, there is no charge here. Okay, therefore this is a more stable one, more stable and major contributor to the resonance hybrid. Okay, more stable and major contributor to the resonance hybrid here. Now here this is having more charges minor contributor, and it will be less stable. Okay, therefore the structure with more bonds and fewer charges, it will be more stable here, correct? And that will be a major contributor, and the other one with more charges, that will be a minor contributor, and it will be less stable here. Here the hybrid will be looking more like A rather than like B, correct? Now another rule we can say is the first one, number of bonds and number of charges, fewer charges will be less stable, more stable than with more charges here. Okay, now a resonance structure with every atom should have an octet. The rule 2 will be an octet rule here. Rule 2, every atom should have an octet, as simple as that thing here. Now if you take a structure of this nature, CH3, say O CH2 plus, a compound of this nature, if you take it, so these electrons, we can go like this to the positive charge. So the structure will be CH3 O plus double bond CH2. Okay, now this will be more stable. Why? Because all second row elements, that is here the carbon, oxygen, they are the second row elements, they have got an octet here. Whereas in the first structure, octet is not there here. Therefore, a structure in which every atom has an octet, it will be more stable. All second row elements here have got an octet in the second structure here. Okay. Then the third one is very simple. That is a structure with a negative charge on a more electronegative atom. Structure that places a negative charge on a more electronegative atom, it will be more stable, because electronegative, it has got a tendency to acquire that negative charge, that is the reason. So CH3, say a compound of this nature, then we can draw CH2 minus. Okay, like this. Here the negative charge is on carbon, and there are two elements here, carbon and oxygen here. Oxygen is more electronegative than carbon, and therefore the negative charge on oxygen will be more stable than on carbon. Okay, therefore we can show it like this. This lone pair, it goes like this. Okay, therefore the structure will be, how it will look like? The more stable structure will be CH3 C minus, the negative charge on the more electronegative atom. So this will be more stable. Okay, so negative charge on a more electronegative atom here. Okay, these are the basic rules regarding resonance hybrid and resonance theory as such. Hope you have understood. So thank you so much for listening.